It's one of the most heartbreaking stories in all of medicine. A patient goes through treatment, the scans finally look good, the tumor is shrinking, and there's hope. But then, months or even years later, it comes back. And this time, it's often stronger, more resistant than before. It's just a devastating setback, and it begs a really critical question.
Why does this keep happening? I mean, if our treatments are designed to kill cancer cells, what are we missing? This is the central mystery we're going to unravel today. And believe me, the answer is changing the entire way we fight this disease. All right, let's dive right in. To really get why cancer relapses, we first have to understand what a tumor actually is. And it turns out the picture we've had in our heads for a long time, well, it was missing a huge piece of the puzzle. For the longest time, we kind of thought of a tumor as just a big blob of identical rogue cells. But the reality? It's much more like a complex, buzzing city full of different kinds of cells. In fact, pathologists have known for over 100 years that tumors look incredibly diverse under a microscope. This idea is called tumor heterogeneity, and it is absolutely key to understanding why they're so ridiculously hard to beat. This slide really nails the huge shift in our thinking. The old idea on the left, called the stochastic model, basically said that all cancer cells were created equal. Any one of them, just by random chance, could regrow a whole tumor. It's like rolling the dice. But the new idea on the right, the hierarchical model, paints a totally different picture. It suggests a tumor is structured more like a kingdom, with a very small, very powerful group of ruler cells at the top, pulling all the strings. And these ruler cells? Well, they have a name. Cancer stem cells, or CSCs for short. The best way to think of them is like the root of a weed. They're rare, sure, but they have this incredibly dangerous ability to just keep renewing themselves and spawning all the other different cells that make up the tumor. So you can pull the top of the weed, which is like the bulk of the tumor, but if you leave that root behind, the whole thing is just going to grow right back. So these cancer stem cells aren't just the seeds of the tumor, they are its ultimate survivalists. I mean, they have a whole toolkit of tricks and defenses that let them withstand the very treatments we designed to kill them. Just look at this arsenal they've got. First, they have amazing DNA repair skills. So when chemo or radiation tries to damage their genetic code, they just fix it. They also ignore the natural self-destruct signals that should kill off damaged cells. A lot of them divide really slowly, which is a clever way to hide from therapies that hunt for fast-growing cells. And get this, even if a chemo drug gets inside them, they have these tiny little pumps that can literally push the drug right back out. On top of all that, they're loaded with enzymes, like one called ALDH, that basically neutralize the toxic drugs we throw at them. And that's the heart of the problem, right? Our standard treatments are actually pretty good at killing the easy targets, the fast-dividing worker cells that make up most of the tumor. So the tumor shrinks and it looks like we're winning. But those treatments often leave the tough, slow-growing cancer stem cells, the roots of the weed, totally unharmed. And the moment the treatment stops, they're free to rebuild the entire tumor all over again. And that's relapse. So, how does this all play out in a real-world clinic? Well, let's zoom in on a specific case. Some fantastic new research from the Mayo Clinic highlights this exact problem in ovarian cancer, which is a really tough one to treat. And it points to a fascinating new way to fight back. Okay, so for ovarian cancer, one of the go-to treatments is a class of drugs called PARP inhibitors. They're smart drugs. They attack a specific weakness in the cancer cell's ability to repair its own DNA. And at first, they can work wonders. But just like our cancer stem cell model would predict, after a while, many tumors figure out a way around it. They develop resistance, and the drug stops working. This is what had researchers scratching their heads. How on earth do these cancer cells adapt so fast? Is it a slow, gradual evolution over many generations of cells? Or is there something else going on? The answer they found was genuinely surprising. The team at Mayo discovered that this resistance isn't always a slow burn. Nope. In fact, almost instantly, after being hit with these PARP inhibitors, the ovarian cancer cells fire up this rapid, pre-programmed survival response. It's like they already have an escape plan. And a key driver, the general leading this defense, is a protein called FRA1. It acts like an emergency override switch, turning on all the genes that help the cancer cells survive the attack. So if the cancer cell has this built-in, super fast defense mechanism, what if we could block that defense before it even gets going? This is where the story gets really clever, and it involves bringing in a drug that was originally designed for a totally different type of cancer. The researchers came up with this brilliant 1-2 punch strategy. First, you hit the cancer with the usual PARP inhibitor. Step 2, just as expected, the cancer cell panics and triggers its survival program. But then, and this is the key, you hit it with the second punch, a lung cancer drug called brigatinib. What brigatinib does is it shuts down two of the master switches for this rapid defense system. They're called FAK and EPH2. With its shields down, the cancer cell is suddenly defenseless, totally vulnerable to that first drug again. And the results? They were just remarkable. The combination was way more effective at killing cancer cells than either drug was on its own. And here's the best part. This powerful tag team effect was seen only in the cancer cells. It left healthy cells alone. That's huge because it suggests a highly targeted therapy that could be tougher on the tumor but easier on the patient. What's even cooler is they found a way to predict which tumors would be most vulnerable. As you can see on this chart, tumors that had high levels of those FAK and EPHA2 survival signals, which by the way are often the most aggressive cancers, they were the ones that got hammered by this combination therapy. This is a massive step toward truly personalizing cancer treatment. So look, this research is more than just about finding a new drug combo. It represents a fundamental shift in strategy, a whole new playbook for how we can approach treating cancer from the ground up. Dr. S. John Waroha, one of the lead researchers, really puts it perfectly. He says, this preclinical work supports the strategy of targeting resistance early, before it has a chance to take hold. It's all about getting out ahead of the cancer. So here's the big game-changing idea. We're trying to move from a reactive strategy to a proactive one. Instead of just hitting the cancer hard and then waiting for it to adapt and fight back, the plan is to anticipate its escape route and block it off from the very start. We're not just fighting the tumor anymore. We're fighting its ability to evolve. And this brings us to a final, really hopeful question. By understanding these hidden rulers of the tumor, these cancer stem cells, and by anticipating their survival tactics, we're not just playing defense anymore. We're learning to play chess against cancer. So what if, just what if, we could finally outsmart it, right from the very first move?